Hi, this is Jason Molesky. In this example, we'll use the conditional probability formula to find the likelihood of an event. Previously, we classified the residents of a large apartment complex based on the events A reads USA Today and B reads the New York Times. The completed Venn diagram is reproduced here. For this problem, we want to find the probability that a randomly selected resident who reads USA Today also reads the New York Times. That is, we want to find the probability reads New York Times given they read USA Today, or the probability of B given A. Well, using our formula, the probability of B given A is equal to the probability of A and B divided by the probability of A. Or in this case, in the Venn diagram, we know the probability of A and B is 0.05, the probability of A is 0.40. Therefore, the probability of B given A will be 0.05 divided by 0.40, or 0.125. So there's a 12.5% chance that a randomly selected resident who reads USA Today also reads the New York Times. For some additional practice with using the conditional probability formula, try exercise 71. Hi, this is Jason Molesky. In this example, we'll take a look at how to use the general multiplication rule and a tree diagram to determine the probability of a particular event occurring. The Pew Internet and American Life project finds that 93% of teenagers use the internet and 55% of online teens have posted a profile on a social networking site. Our problem is to find the probability that a randomly selected teen uses the internet and has posted a profile, and of course we have to show our work. Well, to start with, let's construct a tree diagram. We know that the probability of a teen being online is 93%, and the probability that they have a profile given they're online is 55%. So we can construct half of our tree diagram by indicating 93% to yes for being online, and then from there we have two branches. If they're online, they either have a profile or they don't have a profile. We know that the probability they have a profile given they're online is 55%, which means there's a 45% chance they don't have a profile given they're online. Notice these two have to add up to 1. Likewise, we know that either they're online or not, so these two probabilities have to add up to 1. So 7% of teens are not online, and if they're not online, obviously they don't have a profile. So we have a 100% chance, or a probability of 1, that they don't have a profile, and probability of 0 that they do. Now, to find the probability, we can use the general multiplication rule. So the probability they're online and have a profile is equal to the probability they're online times the probability they have a profile given they're online, or 93% times 55%, which turns out to be about 51.15%. So there's about a 51% chance that a randomly selected teen uses the internet and has posted a profile on a social networking site. For some additional practice in using the general multiplication rule, try exercise 73. Hi, this is Jason Molesky. In this example, we'll use a tree diagram to help us find a conditional probability. Video sharing sites led by YouTube are popular destinations on the internet. We know roughly 27% of adult internet users are between 18 and 29 years old, 45% are 30 to 49, and the remaining 28% are 50 or over. Now, the Pew Internet and American Life project finds that 70% of internet users aged 18 to 29 have visited a video sharing site. 51% of those aged 30 to 49 have visited video sharing sites, and 26% of those 50 years or older have. Now, do most internet users visit YouTube and similar sites? For this problem, suppose we select an adult internet user at random. First, we'll draw a tree diagram to represent the situation. Next, we'll find the probability that the person has visited a video sharing site, showing our work. And finally, given that the person has visited a video sharing site, we'll find the probability that he or she is aged between 18 and 29 years old, again making sure to show our work. Now, to draw a tree diagram, the first thing we'll want to do is draw branches for each of our age groups. We were told 27% were between 18 and 29, 45% are between 30 and 49, and 28% are above the age of 50. Then we know within each of those groups the probability or percent of individuals who visit video sharing sites. 70% of our younger age group visit sites, meaning 30% don't. 51% of our 30 to 49-year-olds visit those sites, meaning 49% don't. And 26% of those 50 or over visit video sharing sites, while 74% don't. Now there are 3 disjoint paths to the video yes, one for each of these age groups. Because the 3 paths are disjoint, the probability an adult internet user visits video sharing sites is simply the sum of their probabilities. Well, to find each of those probabilities, what we need to do is multiply down each of the paths. So the probability that somebody is in the first age group and visits a video sharing site would be found by multiplying 0.27 times 0.7, like we've done here. Likewise, the probability somebody's between 30 and 49 and visits video sharing sites is found by multiplying 0.45 times 0.51, like we've done here, and so on for the age 50 and over. When we multiply those and add them up, we get 0.4913. So we know roughly 49% of all adult internet users have visited a video sharing site. Next, we'll use the tree diagram and the definition of conditional probability to find the probability that somebody is 18 to 29 given they visit a video sharing site. Now, based on the conditional probability formula, we know we can find this by finding the probability they're both 18 to 29 and visit a video sharing site divided by the probability they visit video sharing sites. Now, we found this probability on the previous slide by simply adding up these 3 disjoint paths. What we want to do is find this distinct path, the probability 18 to 29 and visit video sharing site. We know that's roughly 0.1890 by multiplying 0.27 times 0.7. We found the probability that somebody visits a video sharing site overall to be 0.4913, and dividing them out we get 0.3847. So given that the person visits video sharing sites, there's about a 38.5% chance that he or she is aged 18 to 29. Now for some additional practice with tree diagrams and conditional probabilities, try exercise 77. Hi, this is Jason Molesky. In this example, we'll take a look at how to determine whether or not 2 events are independent. Is there a relationship between gender and handedness? To find out, we use Census at School's random data selector to choose an SRS of 100 Australian high school students who completed a survey. The two-way table displays data on the gender and dominant hand of each student. So we can see 100 students were selected total. Of those, 90 were right-handed, 10 were left-handed, 46 were male, 54 were female, and if we look within the table we can see 39 of the males were right-handed, 3 of the females were left-handed, and so on. Let's take a look at whether or not the events male and left-handed are independent, making sure to justify our answer. Well, to check whether the 2 events are independent, we want to find out if knowing that one event has occurred changes the probability that the other event occurs. So suppose we're told that the student that was chosen is male. Well, as we saw, 46 of the students there are male. So the probability somebody is left-handed given they're male is 7 out of the 46, or about 15.2%. Now the unconditional probability of being left-handed is 10%. We get that by noting 10 of the individuals in this simple random sample were left-handed. 10 out of the 100 overall is 10%. Now note, these 2 probabilities are close, but they're not equal. In order for the 2 events to be independent, the probability of being left-handed would have to be exactly equal to the probability of being left-handed given you're a male. So, since they're not the same, the events male and left-handed are not independent. For some additional practice in checking for independence using a two-way table, try exercise 85.